Okay, I'll start recording. Hopefully this time the internet will work all the time. So just before I share the iPad to show you the let me check the chat. I posted the solutions for the quiz of yesterday. So if you go to modules, you'll see now like a module called quiz, and there you'll see the solutions to the different sections of the class. So here I think it's sections 4, 6, and 7. For some reason 5 is skipped, which I don't understand, but so you can check it out there. And yeah, in general, I'll post like the solutions to the quizzes that the day after. Okay. Let's see. I don't think I need to mention right now anything from Canvas. Are there any questions before we start with the lectures? Good. If something comes up, you can always email me. By the way, I don't know if you remember, but we do have office hours before class. The link can be found here on the syllabus. There will also be office hours tomorrow. Yeah, I don't know if there's a group link, but if there is, you can share it. That would be useful. That's a good. Oh, this is something I should have said, so I'll say it. So just to finish the office hours stuff, yeah, the link for the office hours are here, but if you cannot make it to office hours, you can also email me, and usually I'll can give you hints by email if you're stuck with the problem. Oh, good. You can also use a group me, to discuss the problems. If you saw one of the announcements I sent, I think that was on Monday. So we do have some conceptual problems because the grader for those problems is an undergraduate grader. There's like a bunch of restrictions, so they cannot have access. The grader cannot really have access to our official Canvas site. So that's why I have to create like a mirror for our course. So I don't know if everyone has access. I think everyone should have access to a second Canvas site called Conceptual Homework. That's that's more or less the only purpose this alternative site is going to be used. So you don't have to be checking it for announcements or things like that. But yeah. And then, so regarding the question of when is it due, well, you can submit your answers until Monday at 11:59 p.m. It is graded. It is more like graded on accuracy. Here it does. You do need to like get the. It's not just like participation. Let's say. So you do need to get like the answer correct to. Here like it has like 8 parts. It's like 8 true or false. So strictly speaking, if you get like 4 correct, then you get half the credit. But the idea is like each conceptual problems, like each assignment should just take like 5-10 minutes to do. So it should be very short. You can also discuss it with other people in the group. If you want to, you can also email me if you get stuck. But it's just food for thought type questions. So it's not something that should take a lot of time to do. But yeah, like just you can use it as an opportunity to talk with other people about the problems. These you should be able to do after what the material we discussed tomorrow. Between today and tomorrow, you should have like all the tools necessary to answer the questions. Some of you may know how to do them already because I know some know about vectors, or like a large fraction of you. But like, again, like the point is that in general, this will be, not too long to answer. So,
Professor, I just finished linear algebra over the summer, and I think I just want to double check that it's purely a notation difference,
oh yeah,
but the norm or the length of a vector in linear algebra had double brackets on the side.
like the two thing. Yeah, it's sometimes I do write it that way. Yeah, it's not fine. Either way would mean the same. It's just right. If you just use like a single line, it looks more like an absolute value, which may remind you that it is supposed to have many properties similar to absolute value. I don't remember which one the book uses. It's very standard to use the two vars. So yeah, but
are there any other major notation differences that that we should be aware of going from linear algebra?
well, there's a thing which is sort of annoying, which the book does. I don't think that's done like in linear algebra. Like, let me write it on the chat. So like, for example, if you write like a point, right, like 1,0,5, right, you could use this parenthesis. But if you want to write like a vector, which we'll talk about those today, like the book may use different parentheses, like instead of like, I don't know if this is making sense. So like the book sometimes uses like
yeah, right. The pointy parentheses.
Correct. Now, does this really have like any practical? Can there be any issues by like? Could you ever get confused by which parentheses do we mean? No, because like it would always be said like in words. Oh, here's a point P, right? Or here's a vector, this one, right? So it doesn't really matter which parentheses you're using, right? Like whether because like there will be like a word telling you what entity it is referring to. And so, and also vectors will always be written in bold letters or with an arrow on top of them. So that's not such a big problem. That's like the only like thing which may not be the same in terms of notation, like that I can think of. But again, like either this thing with the parentheses or whether or not you want to use one versus two vars, that's not too confusing because there's no other like candidate for what it could mean. And probably you should also, if like the word magnitude or norm would also be used somewhere in the sentence next to the symbol. So it would also be clear that what that's referring to. What I was going to say.
Yeah, that makes sense.
Okay, good. Oh yeah. In general, I think I said this, but I will be uploading the notes of that I write on the iPad to the course site. So for example, since we had this issue last time where like the recording collapsed, I just uploaded the recording from last semester, which was essentially almost word by word what I said like last week. I mean, like life can become very repetitive when you're a professor. So, or you have to teach this a couple of times in your life. So, I mean, not like for comparison, I uploaded both PDFs so you can check them and they're essentially the same. So I uploaded what I wrote in the live version that we had last time, but I also uploaded the PDF for the video that you would see on the course site, so that if you want to follow it. But yeah, if you look at the live version, I think, for example, here. Yeah, like for example, here I mentioned that like, usually for the norm, either of these two are fine and things like that. So, but yeah, like for some reason, like many things in this class have like many different decorations or symbols you can use for it, but they just mean the same. Are there any other questions before we talk about today's material?
Yeah, I have one question.
Yes.
So how close does this course follow the textbook?
Well, in terms of the sections, I mean, it is very close. Yeah, I mean, like usually like the lectures themselves will be some sort of summary of what's in the textbook, presented sometimes a little bit differently. But I mean, the assignments are taken from the textbook and many other things. So it is good to sort of see what the textbook is saying. I don't like, the textbook typically will have a little bit more details than what you need to know if you just want to do well in the class. But it does, at least in how the exams are structured and other things, it does follow it closely. Is that making sense?
Yeah, that makes sense. Thank you.
No, I mean, that's the thing. Like all of these textbooks, they're not like, it's like reinventing the wheel. I mean, like if you open any multivariable calculus course, or book, like it will explain things almost in essentially the same way, right? So the fact that we have a textbook is just to set the pace for which topics are going to be covered for specific classes. But yeah, if you find other books more useful, that's fine. Although I don't think necessarily that like there are that many differences between the different books. Even when they create like a new edition of the book, what they do is just like rearrange things a little bit and like add a couple of exercises here and there. But like multivariable calculus has not changed for at least probably since the 19th century. So you're looking at the material that your great ancestors or whatever would have done, like study. So yeah, nothing to worry about. I'm sure you could look like if you open like the notation might have actually like most of the notation here that we currently use, I think for vectors and things like that was like heavy, like invented by Heaviside, which was like a physicist / electrical engineer. I mean, like those distinctions were not so clear at that time. So like I'm probably like that terminology does not fit very well with what they were doing, like in terms of careers and things like that. But yeah, I mean, it is like old notation, and like many ideas are sort of like the same that they already had. So yes, like, but we do follow the, like, just open the book occasionally. If you have the electronic version, it's a little bit more annoying to open it rather than if you have the book itself. The book itself, the physical copy, does smell nice, in case you are those who have like interest in smelling books, like to see to compare the smells. Like, I mean, they actually do, the smell of a book does depend on the editorial and the publisher company that you're like that made it. So I mean, so good. But yeah, good. Let's switch to, we did have a quiz yesterday. If someone missed it for any reason, well, you can email me about it. But I'm answering. Sometimes I get direct messages. Oh, they were not called like that last time, I think. DMs. Okay, they're using Instagram terminology, I suppose. Or so good. Okay, let me switch to the iPad. Can everyone see the iPad? Good. So just we didn't say much last time. So today, basically, what we're going to talk about is vectors, like, and some operations that you can do with vectors. And by that, I just mean like how to add, subtract vectors. And as I mentioned, like for the first lecture, there's really a couple of ways in which you could multiply vectors. So we're going to talk today about the first way in which you could do this, which is called the dot product. So this is some form of vector multiplication. Roughly, again, this more or less corresponds to sections 12.2, 12.3 on the book. Sometimes, like in a particular section, I may skip some topic and then mention it later. So like, but it's more or less like what you will find in these two sections, what I'll say today. So here are the vectors, if you remember them. Just think of them as some arrows. So as I was saying last time, like the point of a vector is that as long as a vector has two pieces of data, it has like a direction in which it points in space, and it also has a size, right? Like, which is also called its magnitude or norm. So provided you don't change its direction or size, you can sort of move the vector and it is considered the same. So there's like a standard way to represent vectors, which is one where they start from the origin, okay? So the way in which you typically draw vectors. Well, there are two options. In this class, usually we'll work just like what's called like 2 dimensions and 3 dimensions, right? So by 2 dimensions, I just mean X and Y. And by 3 dimensions, I mean like X, Y, Z, right? So basically what we'll say sort of works for 4 or 5, 6 dimensions, but it's just pictures get a little bit complicated. So if you have a vector here, you will draw it this way so that the tails is at the origin, and you the other one, like, well, doesn't matter. Like, let me put it here. And there's this other vector, which let me call it U, which you could draw it this way. So more or less that's how vectors typically look like. And so because of the way in which I'm writing them, so here now the vectors start at the origin, right? And so the tip, the head of the arrow, right? Like sort of where they end, it like gives you a point. So you can use them to specify a point in space. And that's where the vector like ends, right? Like, so here, for example, this vector is specifying the point, let's call it v1 comma v2, or well, you could call it also x comma y if you prefer. I'll call it just v1 comma v2. And this one would be called like u1, u2, u3. So for example, this could be the point 1 comma 5, in which in this case v1 would be 1 and v2 would be 5. Or this could be the point 1, 1, 3, in which case u1 equals 1, u2 equals 1, and u3 equals 3. Is that making sense so far, so good? Now, so typically that's how you draw vectors. Once you have more than one vector, you can add them, as I mentioned. So let me tell you how to add vectors.
Professor,
Yes.
can you please scroll back just for a minute?
Yeah,
Thank you.
sure. So here's a way in which you can add vectors. Say you have a vector u, and then, well, I should. And you have a vector v, and that's, if you wanted to add them together, they sort of have to be brought into coexistence. They cannot be in completely separate parts of space. So since you can move vectors around, you sort of like say bring, you can keep them each at their own places, or you can sort of create like a clone. So let me make a clone of v. Right, this is fine because I'm allowed to move v as long as I don't change its direction or size, which sort of looks fine from the picture. And I'm also going.
Is that because I don't know, this might be a stupid question, but is that because we're working in like a particle system way? Say if this was like a stick and these vectors are acting at two different parts of the stick, we can't really move them, right?
I mean, it's just that like in the end, I mean, before you like the thing is like before like it is convenient just to let's see, how should I say it? They're like, strictly speaking, what you should say is that they're like parallel to each other, right? So like this green vector is sort of parallel to this green vector, right? So like,
yeah.
But in terms of the picture, like you sort of don't want to, but they're a little bit more than parallel, because parallel would just mean that they point in the same direction, right? They're sort of more than parallel because they also have the same size, right? So that's
are you trying to say that these two vectors are trying to move the same point, the origin is just one is acting somewhere in space, the other one's acting somewhere else, you're just bringing them,
right? Like you like,
and say that if it wasn't an origin that they were acting on, it would be a different calculation, I'm assuming.
Right, let's say, okay, this is another way to say it. Like the thing is like the way in which I'm drawing it, these arrows right now, you don't see the origin anywhere, right? I haven't written the origin yet, right?
Yeah, but yes.
So
Okay.
once you draw the origin, then everyone like sort of wants to like say hi to the origin, and they all move to the origin, right? That's sort of like a convention. But as long as there's no origin around, like they're just free in the wild. So you just draw them wherever, you see?
Okay.
It's just like a convention, so it's just convenient.
Yeah.
But right, once they're in the origin, and I'll draw the addition, how it looks once they are both in the origin. But it's just better just to think sort of the vector, because the point is that what you choose as the origin is sort of like arbitrary, right? Like why is this called the origin and not this one, right? Like they're sort of the same under the eyes of God. So like you just want to draw them in a first way where you don't see the origin, but once you put like an origin somewhere, then you can also see how that's supposed to look like.
Okay.
Yeah.
Thank you.
Yeah, sure. So I'm just saying, like, you can create like a clone here. The vectors, the idea is that you put one so that it begins where the other ends. And then the addition is defined just as a new vector that starts at the initial point of one of the vectors and ends at the final point of the second vector. So it looks like this. The idea is that it doesn't really matter how you do this, in the sense that you could also have created a clone of u here and create a clone of v here. And so the vector that starts here and ends here is sort of the same vector that starts here and ends here, which is a fancy way of saying that u plus v equals v plus u. So like the way in which you add vectors, so the way to add vectors is that if you have two vectors, you sort of create a parallelogram, if you want, where the sides are represented by those vectors. And then one of the diagonals corresponds to the sum of the vectors. So one of the diagonals. So again, like what I'm saying is that you just to draw this nicely like here so that it looks more clean, this is sort of what I'm doing. Is that making sense?
Professor, this
Yes.
is the first time I'm hearing of the parallelogram as like a method. Is there any certain advantages that that would give you?
So, sorry, could you repeat the question again? Like you said that this was the first time you heard about this parallelogram thing?
Yeah, instead of tip to tail. And I was wondering what the like advantages would be.
Oh, you mean tip to tail was is that like sort of what I did here when I just drew I didn't finish adding the other two sides?
Yeah.
Yeah, there's no well, okay. The only advantage, if you will, of doing it this way by drawing the parallelogram is that then the natural question it becomes, oh, and what is the other diagonal, right?
Oh, gotcha.
And then I'll tell you in a second what the other diagonal is. But that's the
Okay,
only.
thank you.
Yeah, that's the only thing, because the other one is like the other one you sort of see a triangle, right? Like right, there's like sort of like a triangle for you. And that's all there is to it, right? To a triangle, it has three sides, so you don't ask further questions. But if you draw a parallelogram, you know a parallelogram has two diagonals, right? So you may want to know what is, if there's a fun thing you could do to the other diagonals to give it like a cute meaning or whatever. So, but I'll tell you that in a second. Now, if I'm being honest, like really in practice for this class, when you are asked to add vectors, you're not going to start drawing pictures. I mean, it's sort of nice to know that that's sort of what's going on. The way in which you actually add them for our class is the following. Again, you put your origin somewhere, and now because there's an origin, everyone wants to go there. That's the idea when there's an origin. So everyone like wants to say hi. And if you also move the purple diagonal here, it is like you can sort of draw the pictures. Like, I mean, you could make sure, like, if you drew this to scale, that it actually works the way I'm going to say that it works. But it better be the case that the way to obtain the entries, right, or the coordinates for this point from these two is just by adding their respective entries. You know what I'm trying to say? So I'm just saying that this point would be like U1 plus V1, U2 plus V2. Is that making sense? So like what I'm saying, like, for example, is that if U is like the vector 1, 5, and V is a vector 3, 8, or then U plus V is like what, like 4, 13. And like you don't need the entries to be all positive. It's just sometimes that's easier the first time. So if you had a new vector W, which is like -1, 7, right? Then U plus W would be like what, 0, 12. Is that making sense? So like adding vectors is not that difficult because in practice, like as in like how you are actually going to be, they are going to be presented to you, you just add their corresponding entries. Is that okay? So far so good. Any questions about this? By the way, it doesn't really matter. Also, like a side note, let me, yeah, I can scroll up. I mean, there's most of the time when I do the pictures, I do them on the XY plane just because obviously it's a bit easier for me. They also have like versions in space. So like you could have also like a vector with 3 entries, like something like this, and a vector, another vector with 3 entries, right? Like 0, 1, 7. And you can still add them together, like add them together in the same way in which I did, like entry by entry. And the point is that if this is one vector and then this is the other vector, right, in space, then the third one would sort of be like this diagonal that I'm telling you about. So, I mean, it's just this is a little bit, takes a little bit more time to draw, like. But like, I'm just saying, like, nothing to worry about. Like, you would still say 1, 0, 12. Is that okay? And if you wanted to do, you could even do more crazy stuff, which we're not in general, but you could say, okay, what's like preventing you from like just going on, like, what if you put like 4 entries, right? But if again, this is a little bit, you see, it's sort of like the same. It's just that we're not really going to work with vectors that have like 4 entries in this class. If right, you could not, like, you cannot really draw this last thing that I'm doing here. So, but it's just like mathematics allows you to abstract what you were doing, and so if you could see them, like they would still look like arrows and you would still be adding them the same way. It's just that you cannot really see what's going, I mean, you can sort of see what's going on, but without seeing what's going on, because you cannot really draw them. You would need, you need like a 4th axis, which is perpendicular to X, Y, and Z, right? Sometimes like in physics classes, one axis is like time. And so, but it's still a little bit different because time is not like a spatial direction. Yeah, you can, right, you can still try to make some sort of colors, but it's still, you're still sort of like trying to cheat the system. But yeah, it's true, like they're like different ways to try to represent them. But imagine now if you had like the point is that I could give you like 2 vectors each with 10 entries, and you can still add them together, right? Like, and then and like for big data and things like, well, I should say, like, if you take a linear algebra, you'll find that like all this big data or machine learning, all these algorithms are trying to keep you hooked to your cell phones for hours, so that like the companies keep making money, which is fine, because I mean, it's like a system, capitalism, but how it's supposed to work. But I mean, all these algorithms, like usually like vectors are involved in linear algebra, but like the entries of these vectors will be humongous, right? Like it won't be like 3 entries. Like you'll have like a bunch of input data about the customer, like what their preferences are on the movies or whatever. And so you have to sort of like learn to work with them in a way that does not require you to visualize them, right? But if you understand sort of like the situations where you can visualize them, then like that gives you some insight of what's happening in the general situation. Is that okay? Now, sorry, someone was going to say something.
Yeah, I have a question. Sorry. I'm just curious, what would like the fourth dimension place be? Like, I know it's like X, Y, and Z. What would the fourth be?
Yes, it would be like, I mean, this is like, there's a fun book called Flatland. I don't know if you have heard about it. Let me type it on the chat. Flatland. By Abbott. Again, I think this was written sometime in the 19th century. I mean, the question is similar to asking, like, imagine you're like an insect, right, living on the like just on the top of the book, right, just moving on the XY plane. How would you explain to this like creature what like a third dimension looks like, right? Like, how would you explain what the third axis is supposed to be? I mean, you sort of have to go by analogies, right? But it like, right, this fourth axis would be like supposed to be like an axis which would be sort of perpendicular to all the other three. It's just that you cannot really, you know, it's hard to visualize if all the visual tools that you have at the moment is just like for looking at a 3-dimensional space. But what you should think about is sort of like that in the same way in which you could have like an axis which is perpendicular to the page of the book, right? If you thought of our 3-dimensional space as some sort of like flat surface, then the fourth axis would then be this extra perpendicular axis, right? It's just a little, but it is a little bit hard to visualize. There's a movie about this Flatland. I'll put the link. I don't know if I already put the link on the Canvas site, but it's kind of fun because like the steers are psychopaths. I want to control everyone or something like that. So is that okay? But I mean, it is, yes, it is not obvious, which is why we are not going to go too much into that territory. But yeah, if you take like the thing that you realize later in life as a grown-up mathematician or engineer, scientist, is that many of the ideas that work in 2 and 3 dimensions, you can sort of extrapolate to the other dimensions, despite the fact that you cannot really see them. So is that okay? So
Yeah, that makes sense.
I answered your question without giving you an answer. Because it's like asking, like, you know, it is like, how can you explain an experience that you have not experienced, right? Like, it's sort of like, it is like a difficult cognitive question, but like maybe in the future there will be brain implants and whatever, and they will allow you to enhance your visual system. Who knows? Yeah. So, but the point is that many analogies, I mean, you can sort of work by analogy. So that's like the best idea. Like, you don't really have like a visceral intuition for what's going on, but just by playing with analogies, you can sort of develop some guesses of what's happening. Now, what I was going to say is that what you're not definitely allowed to do, so this is not something you are allowed, is to like say add vectors of different sizes. So you cannot really, if say u is 1, 3 and v is like 2, 1, 0, right? Like they have different sizes. So u plus v, we don't try to define this. Is that okay? So we only try to add vectors that have the sort of same number of entries.
So
Question.
like for this one,
Wouldn't
sorry.
wouldn't the third dimension for say u just be 0?
Right,
Yeah.
right. You can sort of, yes, yeah. I mean, I thought someone would say this. I mean, that's a appropriate thing to do, but then secretly what you did was sort of add like a third entry to you, right? Which was just agreed to be 0, and then you add them, right? But you didn't add you per se as you, right? Just you with 2 entries. Like, but yeah, like in practice, if you really wanted to add u with v, you could, like, for example, add like a third entry 0 to u, yes, and just say that then that's how you're doing the sum. But strictly speaking, you did sort of make them of the same size first, if that makes sense.
Okay.
Yeah, it's a little bit
Does that
pedantic,
al-
yeah, but
Does it also have to do anything with kind of like the amount of data it takes to store a vector that has 3 variables versus 2?
right, like a computer would, I mean, like, I'm sure, like, I never really tried to do this computer stuff, programming stuff too carefully, but I mean, surely, like, if you were trying to actually, like, right, if you were trying to make a program whose input is vectors, right? The computer does not, the computer doesn't know really what's going on unless you think they already became conscious, right? So it does not, like, if the input is supposed to work, right, by feeding vectors with 3 entries, right? And you try to feed it a vector with 2 entries, like the computer will not know what's going on, right? Like you can do then this thing about like adding this third entry to be 0, but that's like another piece of information, right? Because like, then you're storing more information about you. So like, I mean, the same you could do, like, I suppose if W had like a 4th, right? Like imagine this was like 1, 1, 1, 1, 1. Then V plus W would also not be defined, right? But you could say, well, what if you add a 4th entry to V, which is just 0? Yeah, sure, you can do this, but it is something you need to do, right? Like that's all that I'm saying.
Got it.
Yeah,
Okay.
yeah. But yeah.
Thank you.
Sure. It is a little bit pedantic, but it's just something to realize, like that only vectors of this, you sort of work with vectors of the same size at all times. It's just yeah, many times, like, you just implicitly assume that one of their entries is 0, just so that you can keep adding them. As I think someone else was going to ask something about, or maybe it was the same question.
Yeah, I have the same question.
Good. But yeah, you're now thinking how to do this on computers, which is good. I mean, because, like, if you have taken like a programming class, you'll realize that, like, the language, like, just like these small details is a important part of your computer programmer skills, right? Like, just to make sure that the rules are well defined. So now, how to subtract vectors. This is a cute one. Like, for example, how would you subtract numbers? Well, what is 3 minus 5? This seems a little bit silly to do, but you could say, well, this is 3 plus minus 5. Oh, yeah. No, we talked about the MATLAB assignments, but there's still, I mean, there will be posted. I mean,
I tried adding the U and the V that were improper sizes from before, and just to see the error pop up.
Wolf. Oh, good. Excellent. So yeah, but about the MATLAB assignments, there's nothing much to worry about for the moment, but I'll say more about it once in a couple of weeks. The MATLAB assignments are sort of meant to be super easy. So it's almost basically we were going to give you the code and you just copy paste it on MATLAB, make sure it runs, and you get like a cute image. That's what will happen. So now, what is 3 minus 5? It is 3 plus minus 5, which seems a little bit silly, but it's not that silly if you realize that this is a number 3, and then you think of the -5 as being another number just on the left to the left of 0, and then you realize that you can add these two numbers, right? Because you already have a way to add the numbers, and so that's how you get 3 minus 5. So for example, if you want to like subtract two vectors, right? V minus a vector u, that should be the same as V plus minus a vector u. And why is this useful? Because like say, here is a vector V, right? Here was a vector u. Again, now instead of doing V plus u, which we already know, I'm going to work first with minus u. I don't know if you remember that I told you that negative u from last time is just the same vector in the sense that it has the same size. It's just that the direction was flipped, right? And so if you do that, then you do this thing about bringing them together. Remember that one has to begin where the other ends. Oh, let me put it like this first. And so here would be, this is the sum, V minus U. And then let me draw it here so that it's, that's V minus U or V plus minus U. But if you see it from the perspective of drawing the parallelogram, what does this look like? It looks like the other diagonal of the parallelogram, right? So what I'm saying is that, in fact, what happens is that if you draw the original parallelogram with U and V, notice that the only thing that I'm changing is like where like I'm drawing like the tail and the heads of the arrows. The arrow, like if you were to erase the head, like the tip of the vector, then you really would not see any distinctions between these two pictures. So what I'm saying is that one of the diagonals, the one from before, is U plus V, and the other diagonal, the red one of the parallelogram, this is V minus U. Is that making sense?
Yeah.
So the point is, like, we did all of this just to say that the other, so like the interpretation of V minus U is a second diagonal in the parallelogram. So V minus U is the remaining diagonal. So it's the other. And again, in practice, like how would you work with the subtraction? It's not different from before. So you just subtract the corresponding entries one by one. So for example, if you had been 1,5 and V had been 2,7, right? So what is V minus U? It is just, well, what is 2 minus 1? That's 1. And what is 7 minus 5? That's 2. So you just subtract the entries individually. So it's not too complicated. If you had like a different vector W, which was like -1, 1. Oh, yeah. Let's do, good. Let's do, what is U minus V? Great question. What is U minus V? That's 1 Well, that's 1 minus 2, which is -1, and 5 minus 7, which is -2. So it is what? It is minus b minus u. This is a thing that always happens, so let me put it in a box or cloud. Is that making sense? Good, but that's a good like thing to realize. So many like, if you had not written the arrows on top of these symbols, you would have worked with this the same way in which you would like in high school, right? You would not have even realized that something new is happening here. But yeah, in general, u minus v is minus v minus u. Is that okay? Now, why is this useful? Because like, and now we'll talk about this later, next time a little bit more, but sorry, let me just check. Oh yeah. So imagine that again, like you draw this with respect to the origin. So you had the vector u here, which is like a point, represents a point P, which is u1 comma u2. And you have the vector v here, which represents a point Q, call it Q, which is v1, v2. Then like this this subtraction, right? Again, like just copy pasted from the picture here. This red vector was a diagonal. So this was a vector v minus u. But I don't know if you see, like from this picture, maybe it's more clear what's happening. This is a vector that connects the vector, the point P with the point Q in this case, right? Is that making sense? It sort of is like a relative distance vector, because it's sort of like the relative position between from point P to point Q. It's like the vector that you need to travel if you're at P to get to Q. Is that okay? So if like what I'm saying is that if P is represented by a vector and Q is well, then the subtraction, which is the difference between these two vectors, which is v1 minus u1, v2 minus u2, gives you like the vector that goes from point P to point Q. It's a vector. So let me write it in a better way, which may look more similar to how you have seen it before. If the point P has like entries x1, y1, and the point Q has entries x2, y2, right? Then there's this new vector called PQ, which is Q minus P, and this is a vector from P to Q. And it is given by x2 minus x1, y2 minus y1. Is that making sense? So that's like how you would and like, I don't know if you remember, maybe you have seen already like the distance formula for 2 points. Have you, right, like maybe you know the distance formula for 2 points on the plane, right? Like where you just have to subtract, you first subtract the entries and then like do like a Pythagoras theorem. Like, does that look similar? Like this is where it's coming from, right? Because that these are the entries of this vector that gives you like the relative position between the two. So this is like a useful vector that shows up in many places, because in many forces, you know, in physics, the force between two particles depends on their relative position, right? And so this is a useful vector that appears many times. Let me just finish writing this, like, because it's, I'll say more about it next time. But so the distance from P to Q is going to be, we'll say more about that next time, but let me just write it here so that you have it. Which again will, this will actually coincide with the size of the vector PQ, this vector that I wrote here. Is that okay? Any questions about this? Yeah, I was asked to scroll up. I will upload the notes anyways, but so you can finish copying if you miss something. But so like the point is that subtraction and addition of vectors should not be that intimidating. Now let's do something a little more interesting, which is how to multiply vectors. So, and we'll say more about this next time. So this is not all that you'll see. By next time, I suppose it's tomorrow, right? So tomorrow we'll talk more about this, but let's talk about the dot product. Again, like sometimes it has different names, also known as a scalar product or an inner product, although these two other names are not names that we'll use in this course. So usually the name that the standard name for us will be the dot product. But if you take like again, like a linear algebra class or whatever, I don't know, in statistics, this could also have been used. It is not unusual to see these two other names for the dot product. But so like, again, what is multiplication of two numbers? Like say 3 times 5, you get 15, which is a new number, right? So if you have two vectors, you would like to multiply them. Like you might think, well, you may want to get a new vector, right? In the same way in which the product of two numbers is a number. And we will do that next time, which is called the cross product. But for now, the dot product works in a slightly different way. So the way in which the dot product works is that you start with two vectors, a vector u and a vector v. And the dot product is not going to be a number. Sorry, it's not going to be a vector. It's going to be a number. So u dot v, this is going to be a number or scalar. Remember, scalar was the other fancy word for number. So this will be a number. Not a new vector. And so what's this magic formula for the dot product? well, you have these two vectors, u and v. Again, you sort of have to bring them together. Once, like, so you have this vector in space, you have this other vector in space. You bring them together, like, again, without modifying their sizes or orientations. Once you bring them together, there's sort of like an obvious way to talk about the angle between the two of them, right? If you have them like all the way, like, you know, very separated in space, it's not obvious how you talk about the angle between two vectors. But once they're together, then it does make sense to talk about the angle between the vectors, right? So theta, this is the angle between the vectors. Well, you might say, well, what's the angle between the vectors? Because if this is one of the angles, there's another bigger angle here, right? Like what I'm trying to say is that secretly, there's another, you could also say from the picture, oh, isn't this thing, this purple angle also the angle between them? I don't know if you know what I'm trying to say. The point is that we always choose like the smallest of the two options. So like there are always like two natural candidates for what the angle should be, like this one or the other one. And we choose the one where, which is the smallest, which means that it will be between 0 and 180 degrees. So this will be chosen so that it's between 0, the 1, which is between 0 degrees and 180 degrees, or 0 degrees and pi radians. Sorry, 0 radians and pi radians. Is that making sense? So there's always like two possible angles between two vectors, and you choose like the smallest one. So far, so good. So like the picture then does look like what I'm drawing. Any questions up to this point? And once you have all of this in place, then the dot product, by definition, if you want, the way in which it is computed is as the product of the sizes of the vectors times the cosine of the angle between them. This is one of the key formulas in this class, one that you should never forget. So, or definition if you want. So this is how the dot product is computed. Right. You find the length, right? So in words, this is like multiply the length of the vectors times the cosine of the angle times cosine of the angle. Oh, yes, it will be the same, but I'll explain in a second why. But not for now. You don't need to know that coincides with the thing that you're saying. But yeah, they will agree. Each entries, yeah. But yeah, like this is like sort of, think of this as a definition. I'll return to that other alternative way to find it. Yeah. So what I'm saying is that Yes, right, but you'll see that there's a cute way to do this without invoking Pythagoras theorem per se, and I'll also say this in a second. So for like what I'm trying to say is that, for example, if what were the colors? Oh, if this is V, so imagine that V has size or magnitude or norm 6, and imagine that U has size or magnitude or norm equals to 5. And I also tell you that the angle between them is like, say what, pi over 3 radians, which is the same as 60 degrees. Then according to this formula, what would the dot product between the vectors be? It is like you multiply the sizes and you also multiply by the cosine of the angle. So the size of U is 5, the size of V is 6, and the cosine of the angle is the cosine of pi over 3. I don't know if anyone remembers cosine of pi over 3. That should be 1/2. So this is 15. So that's what the dot product gives you in this particular case. Is that okay? Yes, next time. By next time again tomorrow, probably. So far, so good. So here's something important. Whoops. Let's say that the angle between these two vectors is exactly 90 degrees. What can you tell me about the dot product? Good, because cosine of pi over 2 is 0, right? Right. So, well, I'll wait a second to say this. What if the angle is less than 90 degrees? So this is called sometimes acute, right? Acute angle. So this is acute, meaning that the angle is less than 90. Well, we don't know the value itself, but we know, right, the cosine of an angle between 0 and 90 is positive, right? So the dot product, whatever it is, because we don't know the particular sizes in this picture, but whatever it is, it will come out to be positive, right? And well, as you can imagine, the other situation is that what if the angle is obtuse? Meaning that the angle is more than 90, but less than 180, right? So what can you tell me about the sign? So this is a positive dot product. what can you tell me about the sign? Right, it would be cosine of an angle between 90 and 180 is negative, right? So whatever the dot product is, like the actual number that you get, it will be negative in this case. That making sense? So
Professor?
yes.
In the positive side, is it greater than or equal to, or is it just greater than?
It's strictly speaking, I mean, as long as the vectors do have some size, right? It's not equal to, because equal, I'm just taking it to be perpendicular, right? And so, yeah, it's strictly greater. I mean, so by acute here, I mean that the angle is strictly between 0 and 90 degrees. Here, I just mean that the angle is exactly 90 degrees. Well, it could be greater or equal to 0. And here, I mean that the angle is between 90 and 180, and 180 is allowed. Is that better now?
Yep.
Now you could have like a silly situation where like one of the two vectors has size 0, which is called the 0 vector, but let's not get into that. I mean, if it's like as the picture conveys, where both of the vectors have some size, then what I'm saying is fine. Like, you know, there's like a vector called 0 vector, like, yeah, that's a good moment to introduce it. 0 vector is the one whose entries are 0, or 0 vector is 0, 0, 0, right? It has no size, right? So it's not actually like an arrow per se, right? Like if you draw it, you draw like a point. It looks like a point, right? It doesn't look like an arrow. And so in this case, it is true that, like, in a sense, it's that product with anything is 0, right? Is that making sense? And if you add the 0 vector to anything, you also get the original vector, right? So 0 vector is like, I mean, but it's not too clear what's the angle between 0 vector and a vector, right? So like when I made these pictures, I'm assuming that all these vectors have some size. So what I'm saying is fine there. Is this okay? So far, so good. So let me give you some properties of the dot product, and next time I'll tell you how to compute it, because I don't think we only have 5 minutes, and I don't want to. So the first one is that it doesn't matter in which order you write u dot v, meaning that u dot v is the same as v dot u. In the same way in which when multiplying numbers, a times b is the same as b times a. So this sounds silly to mention, but it's important to notice, because once we talk about the other product that we will define, that will not be the case. So it will matter in which order you write them for the next one, not for this one. Okay. Another thing is that, again, like the dot product is what I just said. If it's positive, it means that this is acute angle. if it's 0, it means that it's a 90-degree angle or vectors are perpendicular. Or another, the fancy way, again, of saying perpendicular is orthogonal. So you also call them orthogonal vectors. Which I am never remember if that's like a standard word that people use like in daily life, orthogonal. I think so, but and if it's negative, it's an obtuse angle, right? And the last property before finishing today, oh no, well, I'll say a little bit. Yeah. Let's do this. Like, let's do an application of this. Like, so there are two magic special vectors. Well, let's put them all to. Let's do them all at once, and we'll finish with this. So there are three vectors which some of you may already know and love from your physics classes, which are the vectors called I, J, and K. Anyone? Have you seen them?
Yep.
Good. Excellent. So I is one, has entry 1 in the first component. Yeah, they're like also called, you mean Cartesian vector? I mean, they're called like the Cartesian unit vectors, like if you want like a fancy name, yes. But they're like sort of like useful vectors because they point along the axis of the Cartesian system. Is that making sense? No, what would you say? What do you think is going to be the size of each of these vectors, each of them individually? 1, because only, it has 1 in one of the entries, right? Like however we measure size, it makes sense that their size will be 1, right? Now, what do you think? What's the angle between the different vectors? Like, what's the angle between I and J, or I and K, or J and K, and things like that? They're 90 degrees angles, right? So based on this property that I just told you about the dot product, what do you expect their dot products to be? They should be 0, right? Because they're mutually perpendicular. Is that okay? And just to finish, I'll repeat this next time because I'm under 30 seconds. So what will happen, just like next time, I'll say it quickly. So don't worry if this doesn't make sense. Like what will happen is that, so if you wanted to compute the dot product between 1, 0, 3, just to make it quickly, make this quick, and say 1, -1, 1, 2, right? That will be the same as, the first vector u is going to be the same as the vector I plus 3 times the vector k, and the vector v is going to be the same as -I plus j plus 2k. And then the dot product, if you wanted to do the dot product, this would be like doing the dot product between I plus 3k dot -I plus j plus 2k. And then what happens is that it's like everyone against each other. So you do the dot products individually. But there's a bunch of death because there are many dot products are just 0. So what we'll find is that the only survivors, and I'll do this again next time, so don't worry, is that, like, for example, the only thing that survives of the red ones is I with negative I, because I with J dies and I with K dies. And the only thing that survives from the blue ones is K with K, because K with I was 0 in dot product and K with J was 0 in dot product. So what happens is that you get 3K dot 2K, and you get here, again, I'll do this next time, but you'll get -1 plus 6. This will make more sense next time, but this is how, which corresponds to some, like the question that someone had mentioned on the chat, the way in which you realize this, that this is the same as like just having done 1 times -1 plus 0 times 1 plus 3 times 2. So at the end of the day, the way in which you compute the dot product is just by doing the multiplications of the entries individually and then just adding up the answers. Okay. Yeah, perpendicular ones kill each other. So that's why you don't see them. So originally there would have been tons of dot products, but they all die. And you only get the ones that are like I with I, or J with J, or K with K. And that's why you end up adding the corresponding entries, or orthogonal ones. Yeah. But I'll say this next time again, once we have more carefully. But like, this is sort of like an idea of why things behave the way they do. So tomorrow we'll keep talking about dot products, and if we have time, we'll introduce cross products. So I'll see you. I'll upload soon the lectures and other things. I have another class soon, so maybe after my second class ends, I'll do this. But I'll send an email with a summary. Bye.
Thank you, Professor. Have a nice day.
You too. Bye.
Have a nice day.
See you. Okay, now let's hope that the recording worked this time. Okay.